Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing good. I walked outside from my office to class today, and it felt warm, and it felt wonderful, and I could hear geese honking in the background, and so that's a good thing. That means that summer is definitely coming. It's Pi Day today, and there's an event that's happening this afternoon where at least some math prof, I think, is going to get pied. I don't know where they're doing it, but they were asking for volunteers from the computer science department, and unfortunately for us, for me, for you, I have a class at that time, so I can't get pied in the face, but somebody's going to get pied in the face, so it might be fun to check out if you got time for that. I don't have any more information than that, so just wander around open rooms and see if there's somebody getting pied in the face. Today, what I want you to be able to do is I want to be able to evaluate the performance of some scheduling policies. So we're going to be using this. So I've got this already up on my screen. We're going to be using this. If you're here in person, I've got a printout of this, but this is also up on the course webpage alongside today's notes. We'll be taking a look at mechanically applying some different scheduling policies to this set of tasks, this workload, and then measuring the performance of those scheduling policies on different metrics that we think about when we're thinking about evaluating scheduling policies. Once we've been able to evaluate the performance of some of these scheduling policies on this specific workload, I want to be able to then start comparing and contrasting these different scheduling policies based on the workloads that we've got. So ultimately, different scheduling policies are going to be different in different circumstances. Some scheduling policies will work better for a specific workload, and other scheduling policies will work better for a different specific workload, and they kind of may conflict with each other. Ultimately, the goal that we would want to have from this is to be able to say, this is the workload that I'm expecting, and so I'm going to pick a policy like this one to run these tasks through it. But for us, minimally for today, what we're looking at is I want to be able to take the performance that we got from the scheduling policies for this workload and then compare them to each other. So how does this workload work under this specific scheduling policy? It's Friday, and so I also want to take the time to take a look at what we're going to be looking forward to next week. And so I'm going to pop over here to the course webpage. And I'm going to take a look at the lecture section for next week. And what we're looking at next week is I/O scheduling, and physical representation. So part of this is going to be backfilling some of the hard disk related stuff related to RAID and related to file systems. And part of what we're going to see in this unit is this idea of being able to have this atomic operation of writing a single sector. As you're going through this stuff, there's two things that I want you to begin to think about. And what I'm thinking about is in terms of physical representation, so an actual physical disk and I/O, how is this idea of atomicity related to what we're using atomicity for in terms of concurrency? So we want to be able to have atomic instructions for locks. Is there any relationship between this atomic unit of a sector with a drive and the idea of concurrency synchronization tools that we've been using? And then the other thing that I want you to think about as you're going through this is related to I/O scheduling. The key takeaway that I have for this is kind of related to the idea of what we're going to be looking at this week with scheduling. We're looking at process scheduling, and there are certain assumptions that we're making about process scheduling that are not realistic assumptions to have about processes. I/O scheduling, superficially, seems like it's going to be a similar topic in that there's the word scheduling appearing in this thing, and the idea of scheduling I/O and scheduling processes is kind of related to each other, but the unrealistic assumptions that we have for processes suddenly become realistic with I/O, and so try to keep that in mind as you're thinking about this stuff. There's two chapters here, chapter 36 and chapter 37. One of the things that I'm going to pop over here to chapter 37 and scroll down a little bit here is I'm going to keep scrolling down here, And the part that I'm looking for is this. Yeah, this is the part that I'm looking for. Oh my God, it's calculus, and oh my God, it's physics. I don't care about this stuff. This aside is interesting. It's interesting from the perspective of like, well, I don't know when the last time you did integrals was. For me, it's been about 20 years. So like, it's been a long time since I've thought about integrals, but I don't actually care about this stuff. This is cool to think about, like we can calculate the rotational latency of a disk spinning around on a platter because it's a circle, and then start to think about how to figure out what the distance between two different things on this arc of this circle is, but I don't actually care. I really don't actually care. This is not important for us at the operating system level right now. This becomes important when you're starting to think about hardware, but this is not super important for us. So as you're reading through this chapter, please read this if you want, but also feel completely free to ignore this aside. You don't have to worry too much about this. Next week, we'll also spend a little bit of time taking a look at a physical drive. I'll bring a couple of drives to class, and we'll take them apart and just look at them to see what's going on the inside of this thing. So the other thing I did want to bring up is that I posted a grading guide on the course webpage for the term test. I published those grades to you. I made them available to you yesterday. I'm very happy to talk to anybody if you have any questions about the feedback that you received. I did try to take a look at some of the feedback, kind of random sampling of the feedback that the graders gave, and it looked okay, but I can't look at everybody's feedback for every single question. So if you have any questions, please feel free to reach out to me, and I'm happy to take a look. But there's also the grading guide that I published here to give you some idea of what I was looking for each of these questions. I'm going to politely request that if you use this document, you don't publish it anywhere. Please respect my copyright. This is something that I created myself, but please don't publish it anywhere else. This is just for your personal use. I also wanted to talk about this important topic. You haven't ever seen my cat before right now, but this is my cat. His name is Walter. This is an old photo. He has a lot more white hairs now than he does in this picture. But you know, this is the sort of thing that he likes to spend his time doing, is sleeping on a couch, although his favorite spot right now is my son's bed. And I suspect that's because, one, the sun shines in his room at the right time of day at this point, but also because he feeds him in the morning. Yeah, he's adorable. He's adorable. He's adorable, except when he's, you know, being an old man. And so I wanted to show you some of these things that I liked the best, because I did take a look at all of these ones. There was a couple of this wasn't just once that this came up. This was multiple times that people drew a little picture here that implied that Walter was the reason that the power went out. This one is an angry face Walter saying, "Spoiler, power's going to go out." I liked this one a lot. I really liked this one. There were lots that were like this that I also really enjoyed. It says "Best Kitty" there. There were more than one that made Walter into this formal little thing. I don't know why this also came up. This came up more often than Walter being the one that caused the power to go out. There were a few that showed up that were like Valentine's related, which I thought was funny and relevant to the day that we were on. This one I liked because of just like how ultra realistic the hand is, but then the rest of the body is just like this blob. I like this one because, I don't know, it even matches the shirt that I'm wearing right now, although I don't think I have stick arms. This one was just really nice. I'm going to be honest, and I don't care if I offend you right now. Most of you are terrible artists. But this person did an excellent job. This person did an excellent job. And this one was my favorite. And this was the comment that I gave back to them, because there's Walter here saying, "Oops," and there's a house on fire in the background. And it instantly reminded me of this meme when I saw that picture. So, So thank you all for sharing those drawings with me. I appreciated that. So what I want to do now is I want to schedule us some tasks. I want to go through the process of mechanically applying some scheduling policies and then begin to compare their behavior based on the performance that we're able to measure about these different scheduling policies. I'm not going to tell you about each of these scheduling policies in this list right now. Instead, what I'm going to do is say that these are going to guide us, and then as we start to do the scheduling, I'll describe to you what that scheduling policy is to remind you of approximately what we're going to be doing. But there's 5 in total that I'd like to take a look at. In terms of measuring their performance, I want to measure a few different things. The first one is turnaround time, and the turnaround time is pretty much going to be based on when this task arrived, how long did it take on the wall for it to be done what it was supposed to do. So turnaround time is related less to when it starts getting access to the CPU, but when it actually shows up in the system. You can kind of imagine this as being if you're going to McDonald's for lunch and you enter the restaurant door and you line up, that's when your arrival time is. When you leave the store is when your completion time is. So it's the amount of time that you spent actually waiting around for the whole thing to be finished. The response time is when you first run versus when you've arrived. So if you're going to McDonald's for lunch, this is you show up, the time between you showing up and then getting to the counter to make your order, to ask the person that's working at the counter to get you a chicken McNugget meal or whatever. Those are 2 important metrics here that we want to think about. And then the other one is going to be fairness. Does every task eventually get time on the CPU? And I want to consider this in 2 different ways for each of the policies that we're looking at. First, I want to consider fairness, assuming that all tasks are fair. So if we consider that all tasks are fair, meaning that they will eventually finish, they will finish. We've solved the halting problem and we can say that they will eventually finish. Will all tasks get access to the CPU? And assuming they are not fair, we've put a while one in our code and we are never going to finish. If we've done this, can we say confidently that all tasks will eventually get access to the CPU for some amount of time? Okay, so I'm going to pop open my presentation here, and what you should have in front of you right now is either this presentation or one of these sheets with some sticky notes. And what I want to do with this is I'm going to be the measurement of time here. And for each unit of time, what I'm going to ask you to do is make changes to your system as appropriate. I've put all of my tasks into this incoming workload area. And each of these tasks has a certain amount of time that they're going to take. So task A has 5 units of time that is remaining for it to run in the system, and it arrives at time 0. So one of our unrealistic assumptions in the textbook was that all of our tasks arrived at the same time, but we're going to remove that part of our unrealistic assumptions. As I move through time, what I want us to start doing is measuring things like, and keeping track of things like, when was the first time that this task actually ran? So at what time unit did it start running? And at what time unit did it finish running? So I'm gonna keep track of this, and I want you to keep track of it as well. There's different areas that we have in here. The incoming workload area is going to be, this is the queue of tasks that are going to be entering the system as time is moving on. There's the current task queue here, which is going to be, these are the things that are in the system that are running. They are running right now. They are eligible to be executed on the CPU, but they're not currently running on the CPU. This is our list of tasks. And then this running task, this is our one CPU. We're going to put our task onto that running task area when it is actually running on the CPU, when it holds it. And when it finishes, we're going to move it to the completed tasks area, and we're going to mark down what the time was when it completed. The way that this is going to work is that I'm going to keep changing the current time. We're going to start at time 0, and then I'm going to change it to time 1, and then I'm going to change it to time 2, and your job is going to be to start moving stuff around in your system, and then I will move stuff around in my system, and then we can kind of make sure that everything is the same between us. There are still some unrealistic assumptions that we're going to make about the way that this little simulation is going to work. The first is that stuff like context switching happens instantaneously in our little system. It doesn't cost any time to do context switching. For us to take a task off of the running task and then shove it into the running queue, and then take a task off of the task queue and shove it into the running area, we're just going to say that that takes 0 units of time. It just happens instantly as something shows up. The first policy that I want to look at is our basic FIFO policy, first in, first out. This is a non-preemptive, this is a cooperative scheduling policy. And the idea is that we put tasks into the current task queue, and we take tasks off the current task queue as they are arriving to the system, but we don't preempt anything. We'll never preempt anything in the system. We've got our current time. We've got quantum here. Again, another word for this is time slice. This is the amount of time that we have in a time slice. But that's the setup here. Are there any questions before I start doing it? We're all okay? We all have a good sense of what to do? Okay, all right, cool. Okay, so the current time is 0. What I'd like you to do is adjust your tasks based on what the current time is. There's one task that arrives at time 0, so move it where you think it's appropriate to move it. And then I'll give you 1 second to do that, and I'll do the same thing. Okay, so at time 0, I'm going to say that task A arrives. I'm going to put it first into my current task queue. And at time 0, again, unrealistic here, all of this is just happening instantaneously. At time 0, it's the only thing that's in the queue. And so it immediately gets to run. It will immediately start to run. So I'm going to take task A and move it from the current task queue and stick it onto the running task. And I'm going to change its first run from question mark here to 0 in my system to keep track of that. Does that look the same as everybody else does right now? Okay, awesome. It's now time 1. Okay, good, nobody's doing anything. The only thing I'm going to say here is there's now only 4 units of time left for this task. So 1 unit of time has elapsed, so it got the CPU for that amount of time, so I'm going to give it 1 less amount of time. Now, it's time 2. Now there's only 3 units of time left. Okay? We're good? Okay, now it's time 3. And I'm just going to keep doing this. Now there's only 2 units of time left. Now it's time 4. Now there's only 1 unit of time left. All right. Now it's time 5. There's a few different things that are going to happen in this instance. I'm going to let you work it out in your system in front of you right now, and then I will work it out with you. Okay. The first thing that I'm going to do in this instance is say that there's 0 units of time left for task A. Task A is done. So I'm going to take it off of my CPU. I'm going to put it in this completed tasks area, and I'm going to say that it finished at time 5. The 2 other things that are going to happen in this instance are that task B shows up and task C shows up. I'm going to say that they arrived at the same instant, but I'm just going to put them in this order because arbitrarily B is less than C, and it kind of makes sense to just leave it in the same order that we have here. There's nothing running on the CPU anymore, and so I'm going to take task B, which arrived first in this instance, and say that it is currently running, and that it starts to run at time 5. Does this match what we got? Okay, awesome. I'm going to change the time to 6. And then very rapidly, I'm going to change it to 7, and then to 8, and then to 9, and then, okay, now it's time 10. Here's what I'm going to do. 5 units of time have elapsed for task B, so there's less time left for it to work on the CPU. In this instance, task D arrives here, and I'm going to stick it behind task C because it actually arrived later than task C. Do we take this off the CPU right now? Quick thumbs up, quick thumbs down. Do we take it off or do we leave it on? Thumbs down means leave it on. Thumbs down means leave it on. We're going to leave it on the CPU. We're doing FIFO right now. FIFO is not preemptive. That means that once the task gets the CPU, it will not give it up. It doesn't give it up. So at this point, I'm going to change this to current time is 11. I'm going to leave that task there. I'm going to say that it has done 1 more unit of work. And I'm also going to say that task E arrives. I'm really rapidly just going to do 4 more units of time here. So time is 11, 12, 13, 14, and now the time is 15. There's 5 units of time left for this task. I'll ask the question again, and now I want everyone just put your thumbs down immediately. Do we take this task off the CPU? We don't. No, it's not preemptive. So we're just going to leave it on there. These other tasks just get stuck waiting. They don't get access to the CPU. I'm going to go now to 20 time units. I'm not gonna step through this anymore because I don't think that's valuable at this point. We're going to go to time 20. And so I'll give you 5 seconds to wrap up what you need to do in your system, and then I'll wrap it up in our system together. I gotta say, I kind of love this like little sticky note thing. Like I can hear it, and it's not gonna pick up on the mic, but I can hear that in my ears, and I think it's funny. Okay, so at time 20, we're gonna say that task B has 0 units of time left to spend on the CPU. It's done. And so its completion time is now going to be 20. I'm gonna take this off the CPU. And again, we're going to suspend disbelief here and just say this is all happening instantaneously. Task C is the first thing in our queue. And so it's going to instantaneously get to take control of the processor. And it's going to start running at time 20. Its first run is at time 20. And the other 2 tasks just got to sit there and wait. They can't do anything yet. I'm going to skip ahead a lot. I think we all agree that we're not taking this off at the next quantum, so let's just skip ahead until task C is done. I'm going to change the time here now from 20 directly to 30. We're not going to step through each of these. All right, so at time 30, task C will have 0 units of time left. It's finished. It completed at time 30. It's going to get moved off the CPU. Task D in this instant will get to move on the CPU, and its first runtime is now at 30. I actually want to start to make some observations about this. I don't even think we need to finish it to be able to start making observations about this in terms of the performance evaluation of this policy. The response time that we have here and the turnaround time are both terrible. They're both terrible. For the very first job, it's great. It immediately gets access to the CPU and it finishes as fast as it could possibly finish. There's no difference between the length of the time of the job and the actual time that it finished. But as we're waiting for these tasks to finish sequentially effectively, these tasks that arrive later, their response time grows and their turnaround time grows. And as more tasks arrive in the system, the response time and turnaround time are each going to grow quite a lot as we wait for these other tasks to finish. So we'll finish this off. I'm going to say now it's time 40. At time 40, task D has 0 units of time left. It finished at time 40. I'll pop this over here, and then in that same instant, task E gets to go. And then we'll say it's time 45. And so now task E is finished. There's 0 units of work left. It finished at time 45, and everybody is done. So now that we've got these measurements, I'm not going to go through the painful process of calculating all these numbers out because it's going to take a bunch of time, and I'm confident that you can all do basic arithmetic with minuses and do averages. I will allow you to do that on your own time, but my observation about this is that for FIFO, for first in, first out, turnaround time and response time grow rapidly as the number of tasks are going to be added to the system. Our remaining question about evaluation of this policy is it fair? The state that we're in right now is that I am going to assert to you that all 5 of these tasks themselves individually are fair. They eventually finish. Given that, quick thumbs up, thumbs down. Is this policy fair? Assuming that all tasks are fair. I'm getting a mix of both. Assuming that all tasks are fair, assuming that we can say that all tasks finish, this is a fair policy. Eventually, everybody will get access to the CPU. Yeah.
If, let's say, like, the remaining time difference between tasks, like if the tasks have 50 remaining steps, they might be taking off the CPU for the full time, which wouldn't mean it's fair, I think.
The word fairness here must be that eventually everybody gets access, where eventually is not a value that we're measuring directly. Eventually is just if time starts at 0 and goes off to infinity, at some point somebody will give us access to the CPU. So if we take 50 units of time or we take 5,000 units of time, we will eventually relinquish control of the processor and somebody else gets access to it. It might take a really long time, and our turnaround time and response time for the tasks that show up after that are going to be really, really bad, but eventually it's going to get access to it.
I mean, wouldn't you say that, like, because, like, imagine it's like an office hours of a problem. If a student takes up the whole office hour of time, would that be fair? There's no time restriction here. That is true.
I hope that you're not saying this from experience. And I hope that you're not saying this from experience. Unlimited office hours. That would be cool, but I need to sleep at some point. There is no time restriction. We're just going off to infinity here. eventually somebody is going to give up access. And what we're asserting by saying that these tasks are all independently fair is that they will take a finite amount of time to finish. Yeah.
At least they tell you.
Yes.
Okay, so you said that individual tasks are there. I was going to ask what if a task is going to take infinite amount of time?
Okay.
That will be infinite.
So that's our next question here. Now, what if we cannot guarantee that all tasks themselves are fair? What if this takes, there's no infinity key on my keyboard, so I'll just write empty. What if task B takes infinity units? It spins, there's a while one. If I do that, now thumbs up, thumbs down meaning this is not a fair policy. Is this a fair policy? Yeah, it's not a fair policy in the general case, because if somebody comes along and either mistakenly puts an infinite loop in or intentionally puts an infinite loop in, we're just stuck on that task forever, and we're never going to give access to someone that shows up after that infinitely long task. An infinite amount of office hours with an infinitely long hallway with an infinite number of students. Yeah. Yeah. There's a problem, and I want to say that it's the Hilbert problem. I don't know for sure. Have you heard of this YouTube channel called Veritasium before? Yeah, so he did a video on this, and it's talking really about countably and uncountably infinite numbers, which is something that you would talk about in 3030? Question mark? I forget where we learned about that. Is it 3030? 3030, okay, yeah. But there's a difference between countably infinite and uncountably infinite numbers, which is mind-blowing. It is crazy. We'll diverge here very, very briefly. The idea is that there's an infinite number of numbers, but there's half as many even numbers. But there's still an infinite number of even numbers. Yeah, so you can start to compare them. They're both infinite, but there's half as many in one of them as there are in the other. And yeah, okay. I'm going to Control Z here all the way back to the beginning of my state. We're going to go back to the beginning here. And now what we're going to do is switch to looking at a different policy. The next policy that I want to look at here is the shortest job first policy. So the policy that we were just looking at was FIFO. This was, you basically get to go when you show up. That's the order that you get to operate in. Now we're switching this to be shortest job first. And so now we're going to have to do some manipulation of the task queue that we have, the things that are waiting to be run. This is a non-preemptive policy. Yeah.
Would a priority queue be?
A priority queue as an implementation would work for something like this, where the priority is going to be the amount of time for the task that you know about. Yeah. Okay. So I'll get us started here. At time 0, some things are going to happen instantaneously. So we're going to put task A into our queue. We're going to order this queue now. We're doing a priority queue, as you're suggesting, but there's nothing in the queue. So we're just going to insert it to be the head of the queue. This is the only thing that's in the queue right now at time 0, so it's there. And also instantaneously at time 0, I'm going to say that task A gets to go onto the processor. So its first runtime is going to be at time 0. I'm going to skip ahead straight to 5 units of time. At 5 units of time, we are instantaneously going to record that task A finishes. We're going to move it off the CPU. And now we've got task B and task C showing up. In shortest job first, you might implement this as a priority queue. You might just look at the list that you got and find the smallest one, implement it however you want to implement it. But in this case, we don't put task B on the processor first because it's not the smallest amount of remaining time for its work. Job C, task C here has 10 units, task B has 15 units, and because it has smaller amount of time, we're going to put task C on this on the processor at time 5. So its first run time, we're going to record this as 5, and task B is going to get stuck on our task queue. I'm going to skip ahead to time 10 here. And I'll ask the question one last time, do we take this off the processor? This is not a preemptive thing, so we're not taking anything off the processor yet. But we do need to record that we've spent 5 units of time working on this task. We'll skip ahead to time 15 now. Oh, sorry, and then also at task 10, task D shows up. And task D has less time than task B has. So task B is going to get stuck behind task D here. Task D is going to get to go before task B does. We'll go to time 11. And at time 11, task E arrives. And task E gets to shove everybody else out of the way because it's the smallest task. So there's 4 time units left remaining for C. All of our jobs are currently in our system. 1 job has finished. And we've got this case where task B arrived before these other 2 tasks did, but it just keeps getting pushed back. It keeps getting pushed back. I'm going to skip ahead now to time 15. We'll give you 2 seconds to maneuver your stuff. At time 15, we've got task C is done. And in this instance, we will move it off the processor into our completed tasks area. And task E, being the thing that has the smallest amount of remaining time, gets to go next. Its first run time is 15. And now we can start to make some observations about this. Based on when the task arrives, I'm going to come to you in just a second, if you have a question.
Because at 11 it was 4, the remaining time.
Sorry, can you repeat the question? So yeah, C, I'm going to say, there's a lot of hand-wavy assumptions here. Yeah, okay. A lot of hand-wavy assumptions here about things happening all instantaneously in one go. What we can start to see about this is that the original amount of time that we had for these tasks is informing the response time that we have for them. It's beginning to inform the response time, and it's beginning to inform the turnaround time for them. And so as tasks are entering the system, tasks that have small amounts of time left are also going to have small turnaround time and small response times. Tasks that have lots of time to do their work, lots of time that they need to take to do their work, are going to have much bigger response times and turnaround times. Let's finish this out. So at time 20, we're going to say that task E has finished. We're going to pop it off of the processor. And task D is the last thing that gets to go on. Its first run is at time 20. I'm going to skip ahead to time 30 now. At time 30, our task is finished. I'm going to pop this off. And task B gets to go. And then we'll go to time 45 here. So we'll finish this thing off. And our completion time here is 45. There's 0 units of time left for this task, and we'll move it down into our completed tasks area. Once each task arrives, it finishes pretty quickly relative to the length of time that it was supposed to have. I'm going to ask the question again. So thumbs up, this is a fair system, assuming that all tasks are fair, and thumbs down, this is not a fair system. This is not a fair system, even assuming all tasks are fair. And I have to add one additional constraint. Let's put this back to this state. Assuming that we constantly have more tasks coming in that are smaller than task B. Task B will never get the processor. If every task going forward, we have an infinite number of tasks that are 14 units long, task B will never get to go. Whereas with FIFO, I will come to you in a second, but with FIFO, task B eventually gets to go. It arrived at a certain time, and based on its arrival time is when it gets to go in the queue of the tasks that are running. Even if an infinite number of things show up after it, it will eventually get to go. Yes?
But I guess one good thing about it would be if it's infinity, it will go last.
If it's an infinitely long job, so that then leads us to the second question. If this isn't fair, if we assume that all tasks are fair, given the constraint that if we keep adding more jobs, a task may never get the processor. If tasks themselves are unfair, does that change this case? Is it still an unfair policy? So thumbs down, this is unfair. Thumbs up, it's fair.
Tasks are unfair.
If tasks themselves are unfair, so if some task is infinitely long. Is not fair. It's still not fair. It's still not fair. Because that task, that infinitely long task, and I think I see where your logic is here. The infinitely long task gets stuck at the end always. It will always get stuck at the end. But that also means that it never gets to run. And so it's not fair to that task that's infinitely long. It will never get to run because it's infinitely long.
I guess it's also the task is the most important. That means you're pushing it off to the end.
Yes. Yeah.
How do we know how long the task takes? Like, how long would it run for?
So the question is, how do we know how long a task is going to run for? In this ultra contrived scenario, it's because I told you how long it's going to take. In practice, we can't know. This is that halting problem that we saw last time. We can't know how long a task is actually for realsies going to take because we cannot solve the halting problem. So we cannot confidently say that it will end, and thus we cannot say when it will end. Big O of n of an algorithm and big O of n memory for a data structure tells us the running time of that algorithm. It doesn't tell us the running time of the program that implements that algorithm or uses that data structure. The program itself might have a bug in it. I could build a search of a linked list where I accidentally put infinite loop while one in a C program. But that doesn't change that using search over a linked list is an ON algorithm. It just means that I'm bad at C programming. Yeah. Yeah.
We're comparing that FIFO to priority one that we just did. You said that it's second one's not fair because it has to be it never gets to go. Would we be not able to apply that to FIFO saying the hypothetical last job in this infinite list would never get to go? Because it's like infinite. You could have an infinite amount of things before it and it would never get to go either.
We're spinning off into infinity here. So I want to constrain this with, I'm going to describe it this way. Even though it's an infinitely long list of tasks that we have, eventually the infinite job will get to go if we let this run for an infinite amount of time.
What would it be eventually get to go?
In this case, B will never get to go. If we have an infinite number of tasks plus B, where the infinite number of tasks is a shorter runtime than B, then B will never get to go. It will always be after this infinite amount of tasks before it. But if we have an infinite amount of tasks, like the millionth task will run in millionth order because that's when it arrived. The infinite task will go. If task B is infinity plus 1, it will never get to go because it's plus 1, and it will always be left at infinity plus 1. Its place in the queue never changes. That's the problem that we're identifying here. But we're thinking about infinities, and now it's getting to be a little weird to think about. Task B as the infinite task in a FIFO will get to go in infinite place. It will be the infinite item in the queue, and if we run infinity tasks, it will go at that infinite place. In SJF and shortest job first, task B is infinity plus 1, but we'll never get to infinity plus 1. It's not possible for us to get to infinity plus 1. Assuming we have an infinite amount of time, we will still never get to infinity plus 1 because there will always be a job before it.
Yeah, I guess let's say like the start time for B is like 30. You could say there's an infinite amount of objects between, you could insert an infinite amount of jobs between time 1 and 2, and you'll never reach time 2 because there's an infinite amount of jobs between 1 and 2.
Well, with shortest job first, yes. But with FIFO, we're always adding it to the end of the queue. It's always going to be at the end of the queue. So even if we add an infinite number of tasks, task B still gets to be the second thing that showed up. And so it's going to run second. And then the third thing that shows up gets to run third. So once you have your place in the queue in FIFO, you keep that place in the queue, and you will go at that time. In this case, you don't keep this place in the queue that you have. You're always going to get pushed back further and further and further. Eventually, you will, at McDonald's, and you're waiting in line, people just keep shoving in front of you, and then eventually you starve to death because you can't get to the desk to order your chicken McNuggets, right? With FIFO, you will eventually get to order your chicken McNuggets because people are just going to keep lining up behind you.
It's like ordering a meal at McDonald's and people keep ordering just a single coffee.
Yes, yes.
They just keep getting their coffee.
So I know this pain because I go to McDonald's and get coffee sometimes, and like I just order the coffee and get it instantly as I watch all these other people waiting for their meals to show up. Yeah.
This is real life scheduling.
Yes.
But my question is, maybe this is like a bit more maybe I'm focusing on it too much, but like technically there is that is infinite in computer.
No.
Integer output.
We are thinking, you're right, in practice there is no infinity. There's no infinite time. Like in practice there's no infinity, but when we're considering these policies, we do have to start to think about some idea of infinity, and just in terms of there could be a contrived situation where if our hydroelectric dam never runs out of water and it's able to power this Pentium 233 ad infinitum, there might be a task in the queue that never gets to run because more tasks just keep showing up and keep showing up and keep showing up.
Maybe a computer is running like this right now, and it's been running like that for 40 years.
I don't think so. I think eventually they get shut down. Yeah. Okay, so I'm going to put this back to its original state. What I'm going to say is that on Monday, I would like to continue with one more policy here. And the policy that I want to continue with on Monday is at least shortest time to completion first, because this is going to show us a preemptive policy as opposed to the two non-preemptive policies that we've looked at right now. And we can begin to think about the idea of fairness with relation to this preemptive policy. The other thing that we're going to talk about on Monday is we're going to talk about assignment 3, so that will be available for us to take a look at. So at this point, you should begin to be able to start evaluating the performance of scheduling policies, and you should start to be able to make comparisons between the scheduling policies that we've got in terms of fairness, in terms of their response time and turnaround time. I didn't calculate response time and turnaround time, but I would expect you to be able to calculate that based on what you have written down about the tasks that you have scheduled here. And I'd expect you to say something coherent about the fairness of a policy given a specific workload. That's it for today. I hope you all have a great weekend, and I'll see you on Monday. Bye, everyone.